When we look at the periodic table, the average atomic mass of the elements is listed under the element symbol. The whole number above is the number of protons, but underneath is a number that is definitely not a whole number. And the reason it's not a whole number is because it's an average mass of the atoms that compose that element. If we look at, for example, chlorine. Chlorine has two naturally occurring isotopes, chlorine-35 and chlorine-37. The mass of one atom of chlorine-35 is 34.97 atomic mass units, and for chlorine-37, it's 36.97 atomic mass units. Remember we said that a proton was just over 1 atomic mass unit, and a neutron was just over 1 atomic mass unit. So they're roughly 1 each. So chlorine-35 weighs about 35 atomic mass units. Chlorine-37 is close to 37. 75% and about 24%. Now, when you do the average of something, usually we're dealing with small numbers of things, and so you just add up the masses of all of them. Like if you were trying to find the average mass of a jelly bean, you could take 10 jelly beans and find their masses, add them together and divide by 10, right? We can't do that with atoms because, first of all, they're too small to weigh by themselves, and second, because there's so many of them. But we can use the percentages and do what's called a weighted average. So you take the percent abundance, 75.77%, and you make that into a decimal. You divide by 100, and that's 0.7577. You multiply that by the mass of that isotope, and then you add the fraction 0.2423. You take the percent and you divide by 100, and you multiply by the mass of that one, and you add them all up together, and you get a weighted average. And it adds up to 35.45, and we look at the periodic table, and under chlorine it's 35.45. So this is all written out telling you how to do the average atomic mass. The fraction of isotope 1 times its mass plus the fraction of isotope 2 times its mass, and however many isotopes, you just keep doing that and you add them all up. Let's do an example. Magnesium. 3 naturally occurring isotopes. So we've got 3 different masses, and then they give us 3 different natural abundances. The natural abundances are always going to add up to 100. And we're supposed to calculate the atomic mass of magnesium.
Where do you get the isotopes at? They just tell you? So
They have to tell you. Yeah, this is not something you could figure out from the periodic table. They'll give you this information. The mass of each of them and the percent abundance would have to be given to you.
So the isotopes of an element. So basically there's just different isotopes with different masses of that one element.
Right. So they differ only in the number of neutrons. There are some elements that have 2 isotopes, and some that have 3, and some have 4, and some have more. And there's not really any pattern, and there's nothing in the periodic table that even tells us how many isotopes that element has. And so this is just kind of stuff we have to tell you. But we want you to understand how those averages are calculated. Because we look at the periodic table, and under chlorine, like we said, 35.45. That's the average mass, but there is no one atom of chlorine that weighs 35.45 atomic mass units. It's just like, they talk about, well, that's not normal. Well, is anyone normal? I think probably there's not one person who's normal. We're all on one side or the other of normal, right? Some of us are closer to it than others, but nobody's normal. Right? And so that's the way it is here. This is an average mass. The average mass, though, works really well for us because in any sample, we're going to have gazillions, literally gazillions of atoms. We're not talking about tens of atoms. We're talking about ginormous, mind-boggling numbers of atoms. And so the averages work really, really well. But we just need to learn how to do a calculation like this. So they're going to give you the mass of each isotope, and they're going to give you a percentage. What you do is you take the percentage and you divide it by 100. You just move the decimal point over 2 places. So 78.99% becomes 0.7899. That means out of 1, 0.7899 would be this guy. And then the mass for that first one is 23.99, so we're going to multiply by that. And then we're going to add the next fraction, which 10% is 0.1000, times the mass of that one, 24.99. And then the last one is 11.10%, so that's 0.1110 times 25.98. And so write it all out like that, and then add it up. Forgot my calculator, so I'm going to have to use my phone. So don't forget your calculator for the exam. 0.7899. And don't round these numbers off. Just use them all, times 23.99 plus 0.1000. Doesn't matter if you enter those zeros in your calculator. Times 24.99 plus 0.1110 times 25.98 equals. And this comes out, my calculator shows me 24.332481. This is the average mass. It's going to have the same unit that the masses of each of these guys had, atomic mass unit. Now this, we always need to think about significant figures. And here we have multiplication and we have adding. And so we could go through that whole thing, but I'm going to tell you a shortcut. However many decimal places the individual masses had, that's how many you should report for your final answer. So each of these had 2 decimal places. It was to the nearest 0.01. So I'm going to round this to the same place, and I'm going to call this 24.33 atomic mass units. And just like when you take the average of the mass of 10 jelly beans, this mass has to be between the lowest and the highest value, or you did something wrong, okay? We can't have the average mass of these be 50 atomic mass units, right? Because they all weigh less than that. But sometimes weird things happen between you and your calculator. So just look at your answer and say, does it make sense? This should be in the same ballpark as these guys. It should be between the highest and the lowest. Any questions? And that's the end of chapter 4. At the end, there's always slides, chapter in review. Gives you some of the most important ideas.